Hi. I'm so sorry. It took a little bit time to make the new podcast. Today I would like to talk about camera calibration and what elements are needed to calibrate a camera, and we will do also an experimental test with a camera, and we find out how we can get the parameters, the camera matrix, for example, parameters, and other coefficients by running a Python code and taking some images from a chessboard, and then find out what are these parameters for camera. And I will try to explain all the theory first, what are the theories, and then we will talk about the experimental part and writing Python code. Of course, I have not written the Python code by myself, but I had to a little bit work around and find the optimal way of running the code. So I will share everything with you guys, and I hope that you enjoyed this video as the camera calibration. Let's do it.
All right, let's do it. I would like to talk about a little bit about the theory, and I found that actually here in MATLAB or MathWorks website a very nice explanation of what is camera calibration. Basically, a geometric camera calibration refers to camera resectioning, which is somehow estimating of the parameters of the lens and image sensor of an image or video camera. And what do we want to do with these parameters is just to somehow correct the lens distortion or measure the size of an object in volt unit. And why we do need that? Because of the applications in machine visions or robotics, you need always to know the you need always to somehow measure the size of the objects at distances. That's the reason that your camera needs to know these parameters in order to basically handle the measurements of those distances or parameters that you need in your application. So for example, as you see here, you see there's an image here which is somehow distorted, and after the camera calibration it is completely straight, so no bending on the edges. As you see here, there is completely clear. Also in estimating like depths using a stereo camera, measuring planar objects like this one, to just estimating the diameter of a coin, and other application in real world, like mapping, and in robotics, autonomous robotics, for example, you need always to map the real world and measure. So that's the reason that it's very important that your camera to be calibrated based on the parameters, optical parameters. So I would like just to tell you that MATLAB or MathWorks has developed itself a tool so-called camera calibrator, but basically it's not free, and you have to pay for this basically tool because it's a part of MATLAB. But I would like just go through this text and to just show you the theory and what are these matrices. And later we will, as I promised, we will use a Python code, a free Python code, to somehow estimate these parameters. So there are two types of cameras. So basically pinhole camera and fisheye camera. Pinhole cameras are very easy or simple type of cameras, and it considers that the lens, there is no distortion in the lens, and basically has usually a narrow field of view or the angle. On the other side, fisheye camera is not like that. Fisheye camera is considered to have a broader wide angle view and can be up to 195-degree field of view or angle view, and it is more for panoramic capturing of the images. And it gets a little bit harder to calculate the parameters for a fisheye camera, but we will go a simple way with the pinhole camera, and we try to find out the parameters. So as I said, the MATLAB itself has a tool that's called camera calibrator, which you can get use kind of pattern that's called chessboard. It's basically exactly like a chessboard, and you can use that as a reference to calibrate your camera. And I will show you later what I mean by a chessboard picture. But let's focus on pinhole calibration algorithm. Pinhole calibration algorithm was based on the model proposed by Jean-Yves Bougout. I hope that I pronounced his name correctly. And it considered the pinhole camera model and lens distortion. As I said, the pinhole camera does not account for the lens distortion, and also because an ideal pinhole camera does not have a lens. However, in this model, we will consider that there exists, with our Python code, there exists distortion, and I will explain later what are these distortion. But if for example, what is a series? So if you take a photo by your camera, there is a 3D object, and this 3D object is reflected on a virtual image plane, which is usually the front side of the optics, and then the optics will convert this build or a camera image to on a detector module, so where the pixels are basically, and which is usually upside down, but standard cameras does not they can be corrected by mirroring basically, and get the right size or right orientation. But this is the simplest way. So you have a 3D object. So if I want to explain a little bit more, so every 3D object has 3 axes, right? X, Y, and Z. And this object, wherever it is, should be somehow, if this is your camera, should be somehow converted to the orientation, or what called so orientation regarding to the camera of the your camera coordination. So there is 2 things happening. One is that this 3D object needs to somehow translated, so somehow transform to this coordinating system, and there are so it means that it needs somehow to get rotated, and rotated based on the camera rotational coordination system, and also it needs to be translated, so transferred, so you have 2 basically, translation and rotation. So these are the main issues or main parameters that needs to be taken into account in order to find out what are the camera metrics. So this translation and this rotation needs to be find out in order to be able to be applied on the camera. So so as you see in this picture, for example, the 3D object was converted to a 2D image. So basically, from a 3D object, we will convert it to a 2D image. And here is also nicely is written that we have a camera. And this camera matrix is built by two matrices: intrinsic matrix, which is internal parameters of this translation. So it means that from here to here, intrinsic transmission, and from here, this imaginary virtual image plane to the 3D object is the extrinsic. So it means rotation and translation on the to the virtual image plane. So two parts: intrinsic matrix multiply extrinsic matrix. It will make our camera matrix. I hope that I'm clear until now. So two parts. And here, as you see, again, the volt point has its orientation and coordination, and it's using this extrinsic matrix translated to the camera coordinating system, and then from there, intrinsic matrix can happen to translate it to from a 3D object to a 2D image, basically, that is readable for the camera. And so this translation is from from volt coordinates x, y, z to camera coordinates x, c, y, c, z, c, and then to 2D coordinate, which is basically x and y coordinate. And extrinsic parameters, as I said, is a multiplication of two matrices: rotational and translational matrix. I will show you later in Python what I mean by that. And then we have intrinsic parameters, which considers focal length, which considers optical center, which considers basically size of the pixel in volt units. For example, you have to calculate basically 5 parameters, and I believe we also will obtain that. I will show you later the intrinsic part of the matrix, and the next things that will be calculated later also in our Python code is the distortion. As I said, in pinhole model we don't consider a distortion in lens, but we can have it. And distortion is usually like that. So either it is pincushion distortion or it is barrel distortion. Pincushion distortion, it looks like that. It's like that, and the barrel distortion, the edges is like the barrel. And if we do not have a tangential distortion, just have a radial distortion, the parameters looks like this equation. So we have basically 3 factors: K1, K2, and K3, which are radial distortion coefficient of the lens. I think in our Python model we will also have this radial distortion. And tangential distortion is like that: if you set up your camera and your chessboard pattern not to be perpendicular and to be tangential, it can have tangential distortion. So this is also one other factor in tangential distortion, which considers P1 and P2, which are the tangential distortion coefficient of the lens. So by saying that, I think it's enough for theory, and I would like to now go review with you guys how to set up my camera, how to set up my chessboard, and taking some photos. And after that we will go to the Python. Okay, all right, let's do it. All right, so I have made a video and I will share you with you guys how did it. So I set up my basically camera, and as I said, I just made a chessboard, and I use another. I didn't have. I should have printed, but I was lazy, unfortunately. And so what I did was like just measuring how big is actually this chessboard that I have put it. It's almost in 6 and 9, so 9 centimeter in 6 centimeter, and you have to have basically this value in order to be able. But basically the most important thing is that to count how many corner in this image you have, so in the row and column. So for example, in the column I had 9 or 10 corner, and horizontally I had like 14 something. We will go into the details. So I will keep it as you see. I keep the camera fixed in one place, and I try to take some photos from different orientation from this chessboard. So it's not really optimal way to get the photo. That you see, it shakes the camera, but still the result was satisfactory. So as you see, I changed the position of the chessboard. I take photo again and different orientation in order to be able to my code, or the code that I was written. I had copied and written and made it optimal in order to be able to basically detect these edges or the corners, and later we can transform this probably in the code in order to find out the parameters, intrinsic parameters, camera parameters, camera matrix parameters, and also coefficients. So that's it. So I think now you know, guys, what I did it in order to take the photos, and now we can go to the Python code and see the results. All right. All right, let's go now doing the coding side. I opened my PyCharm. I use PyCharm for Python. PyCharm community basically is a free version of this editor, and it's very for me easy to work with. I'm not really expert in anything, but I'm just curious to find out how it works and how to do the programming and how to build the stuff. Anyway, so as you see in this photo, I have taken basically 3 photos from all those photos, and basically I made here as you see after link side, I have basically made a folder, a calibration photo, and I have put 3 basically images, 0, 1 and 2, and they are from different angles, different position, and different distance from in regard to my camera. So I have put all these 3 images inside this folder, and then I run this code, which, as I said, I didn't write it myself. I have to give credit now to one website. I hope that you guys can see this website. I definitely need to share it with you because it is important to yes, just a moment. I hope that I can share. Yeah, so there is a website as geeks4geeks.org, camera calibration, and I think this article was written by Priya Rajit. I hope that I pronounce her name correctly. And if you run this code, you will I had problems, so I had to reorder some part of the text in order to be able to implement it. But when I basically run this code, considering when I run this code, considering, let's go back to again, just a moment, I have to go back to yes, okay, So it's a Python code. Okay. I run this code one more time. I hope you guys you will be able to see this. So I run it. As you see, I really hope that you guys see it. Um, so you see that the code basically. Just a moment. I think I've got. I have to show you guys. So yeah, you see that the image so basically tries to find the corners, and for image that was for image 0, and then this is for image 1, I guess, and this is for image 2. I'm really sorry, it's the size of the window is very big. It does not it cannot show you all. I think you see in the corner how it tries to find the corners of each board, and at the end, when this is you want to have the yeah, so we want to have basically the parameters. I hope that I can find the parameters. Just a moment. How can I active? All right, I could come back to here you can see that the code can basically calculate the camera matrix for each tree picture. So we have the camera matrix and tree column, tree row. We have distortion coefficient, which we have basically 5 parameters. I think if it could be the radial distortion and also tangential distortion. I'm not sure. I have to somehow spend more time to check if that is working correctly. I don't know. And then we have one rotational vectors which here, and one translational vector which is also here. So basically yeah, so it includes all those things that we need to consider or calculate the camera matrix. So for all those 3 pictures, the calculation is made. As I said, I don't know, I have not really tried to check if it calculates correctly or not. I do recommend, if you guys want to basically implement this, print out the chessboard like a paper based, not use my, for example, mobile or tablet, and use it, like then you can basically measure exactly how much is that. And I think that we can also look inside the code. So basically you need a CV2, so which is basically CV, OpenCV. You need a NumPy, and that's it. You need these 2 libraries, and then you need to define how many corner points you have in row and column, and then it tries to find the 3 points, 2 points matrices, and also use other functions that is needed, for example, to find chessboard corners, and then it also tries to draw chessboard corners, and at the end there is a matrix which calculates the R vectors, translational vector, radial, rotational vector, distortion matrix, camera, and etc. Yes, and then you can print it out and have these numbers. All right. I hope that you enjoyed this podcast this time. I think it took a little bit longer, but I had to go through every steps, theoretical step and also practical steps, and you get some numbers. As I said, I don't know. I highly like recommend you get also for evaluation, install a trial version of this MATLAB camera calibrator. It works perfectly, because I have heard from the academics that have tried and tested. And you can also test and see if this code is really useful or not. And you can comment and let me also know if it's working or it's not working. Anyway, I hope that you guys enjoyed, and until the next episode, yeah, stay safe and peace.